Okay, so my name's Peter. I'm going to be talking about a paper that is in the works right now with two collaborators, Xavier and Yushi here at Stony Brook and Pete Winkler at Dartmouth. And it's a very different kind of math, I think, than most people at Stony Brook do. So if you've seen other people talk about things, this is not geometry, so if you came for geometry, sorry. We're going to start with the puzzle. Here's the puzzle. So Xavier and Yushi run a random race. So this is how it works. First you pick a continuous probability distribution, mu. And the two runners, Xavier and Yushi, begin at 0. And each time they draw independently from this distribution. So Xavier chooses xi, and Yushi chooses yi, and they both advance that amount. So after n time steps, Xavier wins if he is ahead of Yushi at the end of the race and also at the end of every step. So that means that the sums of all of the xi's has to be greater than the sums of all of the yi's for every k until we get to the end. And the question is, what's the probability that Xavier gets the prize? So does everyone kind of get the puzzle? Okay. So here's an example, just in case you don't. So they both start at 0 right here, and after one step, Xavier's here, 2 steps there, 3, 4, and y is always behind x. So in this case, this is an example of x winning. But if this y3 had been here above x3, then x would not have won. Get the idea? Okay. So part of this, I'm going to kind of explain how the three of us came to this question and also how we went about solving it. Because this is actually not the puzzle that we started with. So oftentimes in research, the thing that you end up with is not the thing you started with. So I'm going to take a step back and say a little bit about the background, how to solve problems like this, and some of the notation that's used. So the first thing we need to talk about are partial orders of vectors. So I don't know if you've seen partial orders before, but partial orders on a set are a relation that says which element is bigger when you give 2, and it's not always true that every 2 elements are comparable. So that's what it means by partial. So if x, which is x1 through xn, and y, which is y1 through yn, are vectors in Rn, then the coordinate dominance order says that x dominates, or coordinate dominates y, and it's written like this, x greater than y, if every element in x is greater than the corresponding element in y. And this is pretty, pretty natural. And so you can see that not every 2 vectors are comparable. For example, the vector 1, 0 and 0, 1 are not comparable. Right? So that's one partial order on vectors. And another one is the majorization order, which looks a little bit more similar to the puzzle. And it's, so vector x majorizes y, and we write it like this with this little triangle, if all of the partial sums of one vector, or x, are bigger than all of the partial sums of y. So all of the corresponding partial sums. So here's an example. So 1, 2, 3 is majorized by 4, 1, 2 because 4 is bigger than 1, 5 is bigger than 3, and 7 is bigger than 6. But, and 5, 2, 3 is bigger than, it's just coordinate dominates 4, 1, 2 because 5 is bigger than 4, 2 is bigger than 1, and 3 is bigger than 2. Okay? Got it? And so now we can reformulate the puzzle. So if x and y are vectors that are chosen, or whose entries are independently chosen from some probability distribution mu, then we want to know what's the probability that x majorizes y. So take that big paragraph, shrink it down to one line. So hopefully you can remember that. The next tool we're going to need are these up-down sequences. So an up-down sequence is just a sequence of ups and downs. U is up, D is down. And there are a couple of ways that we'll view such a sequence, but one interesting one is a mountain valley diagram, a picture with ups and downs, beginning at the origin 0, 0, and consisting of steps either over 1 and up 1 or over 1 and down 1. And there are two types of up-down sequences that we're going to use. So type 1 sequences end on the x-axis, and type 2 sequences stay non-negative. So here's an example of neither type of this sequence. So this first U corresponds to this first up, down, 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 up, down, down, up. And it's neither type 1 nor is it type 2 because it does not stay non-negative and it does not end on the x-axis. Okay. So first thing for some reason, I'm not going to tell you why yet, but for some reason we need to understand more about these up-down sequences. And so here's a proposition. It's a purely combinatorial proposition. There are exactly 2n choose n sequences of length 2n that are type 1. So there are 2n choose n sequences that start and end on the x-axis. And there are also exactly 2n choose n sequences of length 2n that are type 2. The first one is kind of obvious. The second one is not so obvious. And the third fact is that there are exactly 2n choose n over 1 plus n, 1 over n plus 1 sequences of length 2n that are both type 1 and type 2. So in the intersection of these two is this smaller by a factor of 1 over n plus 1. And so we're going to prove this. Does anyone see the proof of the first one? Yeah.
So you would need like 2n of the u's and the d's, and then like of those n of them are u's, so it's just choosing n u's out of 2n.
Exactly. So we can just choose any of the 2n positions to be d, and the other n have to be u because they have to start and end at the x-axis. Great. This second proposition, or the second fact, is significantly more convoluted, not convoluted, but hard, what was you saying? Involved, yeah. Even though it's pretty simple to state. And the proof is actually by a bijection between type 1 and type 2 sequences. So I'm going to show you the way to take a type 1 sequence and turn it into a type 2 sequence, and I'll leave it to you to prove that this is a bijection. So yeah, so we're gonna start with a type 2 and turn it into type 1. So type 2 sequence, we're going to break it into minimal length sequences that start and end at y equals 0. So anytime the sequence crosses the x-axis or even touches it, we break it at that point. So here's an example. So the first time this sequence touches the x-axis is here. There's a little arrow notated. It touches again here, and touches again there. So this is one chunk, this is one, this is another one, this is therefore. Now every piece that's below the x-axis, we're going to reflect up, but then we're also going to change the last up, which becomes a down, back into an up. So for example, this down, down, up becomes up, down, and now instead of down, it goes up. Okay. This down, up becomes an up. So we reflect all but the last term of negative segments. And this happens to be bijection between type 1 and type 2 sequences. And it's the easiest way to prove it. So how about the third one? That there are exactly 2n choose n over n plus 1 sequences that are both type 1 and type 2. And does anyone know what these sequences are called?
The Catalan numbers.
Yeah, the Catalan. Yeah, so they're Catalan numbers. So the nth Catalan number is 2n choose n over n plus 1, and famously counts these sequences. If you want to be able to prove this, you can set up a recurrence relation with the CNs and show that this number satisfies the same recursion that the paths must satisfy. That's how you can establish it. Or you can do some business with generating functions and figure out coefficients. But I'm not going to do that, so here's just an example. There are 6 choose 3 over 4, so that's 5 length 6 up-down sequences of type 1 and 2. So these sequences all stay non-negative and start and end on the x-axis. Okay, so now let's get back to the question, which is how do we solve this puzzle? And as is common, before we solve the actual question, we're going to try to solve easier questions that sound really similar. So the first one is really, really easy. So if x and y are chosen uniformly, so each element of x and each element of y are uniform random variables on the interval 0 to 1, what's the probability that x coordinate dominates y?
0.5? Or...
Well, this is from the
Oh,
end.
so 1/2 to the end.
1/2 to the end, yeah, exactly. And that's pretty obvious because each of the n coordinate pairs are independent. So we have n independent 1/2, so that's 1/2 to the end. The second one's a little bit less obvious. So we're going to take x and y from the same distribution, each element chosen uniformly random from the uniform. And now we want to know what the probability that sort x dominates sort y. So we sort the entries into increasing order, and then we ask the same question. Does anyone have any guesses for this one? It's a little bit less obvious, but you can just call something out if you want to. Yes, no? Here?
Is it the same thing?
Nope, it's not the same thing, but I applaud your courage to say, because if you had been right, then everyone else would have seemed really stupid, because, yeah. Anyway, so the answer is 1 over n plus 1, and it's a little bit less obvious why, but it's going to use the things we just talked about. So here's the way to prove it. So we're going to do a proof by example, and you can see how this generalizes. So let's say we take two independently chosen vectors from this uniform probability distribution, x and y. And what we're going to do is we're going to combine these two vectors into one vector, and we're going to sort that last vector. And then for each element in T, we're going to put a U if that one belonged to y, and a D if it belonged to x. And if you think about this for a second, the property that sort y is less than sort x is the property that the downs always stay above the ups, or the ups always stay above the downs, depending on which one you pick. So the probability that y is coordinate dominated by x is the probability that t prime, that this up-down sequence is type 1, given that it's type 2. So it's the proportion of type 1 sequences, it's the proportion of type 2 sequences that are type 1. And we said that there are 2n choose n over n plus 1 type 1 sequences that are type 2, and overall there are 2 entries in type 2 sequences. So I thought this was kind of cute. Okay, so next model. If there are any questions, interrupt me. Yeah.
So can we go back? Why isn't it type 2 given type 1? Because like there's like equal parts u and d, so I thought like we were working with type 1 and like we were seeing how many are type 2 from that.
So let's see, go back here. So type 1 end on the x-axis, and type 2 stay non-negative. So let's see, I always forgot which one's which. Type 1 such that t prime is type 2. Wait, you might be right, I may have flipped that. I'm pretty sure that's this way though, because, yeah, this is correct. So, we want the condition that you stay positive, conditioning on the fact that you start and end at the same place, because one of them is always a given.
But like you're going to stay at the same place if it's type 1.
Type 1 means you start and end
And
at
the
the,
x-axis.
yeah.
Is it?
Yeah, okay, you
No,
know what, yeah, this might be a typo, like, they're symmetric, so there's a bijection between type 1 and type 2, so yeah,
The
that might
point
be
is,
a,
I think always here, the number of positive up and downs are the same. You be always sure about that.
yeah.
Yeah,
The
so the up
condition
and
that
down
we
are
want,
always
yeah,
the
it's
same,
just
so that's
if-
type
Yeah, so, okay, yeah,
Yeah.
sorry, so this might be type 2 given that it's type 1, yeah,
Okay.
Okay, so what's the next model? And this is actually the model that we started playing with, and then we realized that there was so much more. So we're going to take ui and vi to be uniform random variables on the interval 0, 1, and then we're going to, instead of looking at partial sums, we're going to look at partial products. So the ith coordinate of x is going to be the product of u1 through ui, and same thing with the v's for yi. And then we want to ask again, what's the probability that x coordinate dominates y? Any guesses for this one? Well, that's okay, we didn't have one either. So we've got to do some work for this. And the first thing is this cute little fact about uniforms. Does anyone know this? So if you take two uniform variables, and you divide them, and you condition that the ratio is less than 1, then that ratio is actually uniform. 0, 1, which is,
So what you would do is you're selecting u and u prime from u 0, 1. And then you throw out the results if u over u prime is greater than or equal to 1. So you're only looking at a subset of possible quotients.
yeah, so it's this event. It's
The probability.
u over u1 given that u over u prime is less than 1. Yeah. And there's a cute little argument of why this is true. So if you have a square, this is kind of your state space for all your u's and u primes. Now I just need to remember which one it is. So here we'll have u and here we'll have u prime. So if u over u prime is less than 1, then you are here, right? Or here? Sure. Here, yeah. So that means that the proportion that you care about is this. But the total number that you could get is, this whole big triangle. Right? So when you pick u and compare it to u prime, the ratio of this area is linear with respect to this whole area. So it's also uniform. And now we're going to translate the language of greater than or less than into ups and downs, just for ease of notation. So if xi is greater than yi, so if the first product of ui's is greater than the first product of vi's, then that element of the sequence is up, and otherwise it'll be down. And here's where a little bit of the abstract nonsense starts, but we're going to let wk denote this event, that xi is greater than yi for all I up to k. So wn is that you win, but wk is that you've won up to the k time. And we're going to let m sub n of s be 2 to the n times the sum over all of the sequences, all of the up-down sequences that start with s. So s is given, but the probability that you win, given that you start with some particular sequence. Okay? And lastly, we're going to let n sub n of s be the set of type 2 up-down 2n sequences beginning with s. And these might seem kind of weird, but the reason that we multiplied by 2n here is because the probability of this happening is always 1 over 2 to the n. So this 2 to the n here turns this into an integer. And this n sub n of s is also an integer. And the point is that we're going to show that m sub n of s and n sub n of s are used in the same recursion. And then we're going to show that they're the same by showing they satisfy the same recursion. Or something kind of like that. So the first recursion is that P of Wn, so the probability of winning, given that you start with KUs and then a D, and then something else, whatever it is half the probability of winning up to n minus 1 if you start with KUs and then some other fixed S, plus 1/2 the probability of winning up to n minus 1 of UK minus 1 and then a down, and then an S. So we can remove this U, the kth U, or we can remove the D and then sum these probabilities half and half. Okay, so this is the first recursion, and this is proven just by going back to the definitions and using this ratio of uniforms lemma. And the next thing is we show that Mn UKD is equal to Nn UKD. So, like I said, we show that these satisfy the same recursion, and so they're actually equal because they have the same base case. Okay, now let's get into the proof. So this is kind of long and annoying, but just want to go through the steps. So we want to find the probability that y is less than x, and that event is called Wn. So if we sum over all of the possible up-down sequences that result from this ratio, or the partial products of uniforms, and comparing them, then we can expand this probability in conditional probability here. So this is just an inequality over all the different things that could happen. And like I said, P of S is always 1 over 2 to the n. So we can pull that out. And then we can split this further into how many U's we start with. And we have to start with at least 1, because if you don't start with 1, then you lose, right? You have to start with a U. It's possible to start with a U and then have a D and still win, but you have to start with a U. So we sum over all of the possible numbers of starting U's, so we know exactly what this thing, well not exactly, but we know more information about what this looks like. But this quantity here is just Mn UKD, which we proved on the, I said on the previous slide is equal to the cardinality of this set. And we got an extra 1 over 2 to the n from this definition, so that's why there's now 4 to the n here. But this last sum, if we think about what this is the number of type 2 sequences that start with k ups. But we're summing over all k, so this is just the number of type 2 sequences, which we said, wait, at the beginning was 2 entries n over 4 to the n. Right. Any questions about this? I tried to make it digestible, but you might not care, that's all right. Okay, so next, so what have we taken? Let's take stock of what we have so far. So we have that if you just take vectors chosen uniformly and compare them coordinate-wise, it's 1 over 2 to the n. If you sort them and then compare them coordinate-wise, it's 1 over n plus 1. And if you do this partial products thing, it's 2 to the n over, I had it here, 2 to the n, choose n over 4 to the n. So 3 different answers. And really what's going on is that there are different situations, there are different partial orders, and we're getting different answers, so we expected that. But then we saw this, and this was weird. So keep in mind 2n, choose n over 4 to the n, that's the answer for partial products of uniforms. Then we thought about the exponential distribution. So let's change the game. Instead of taking from a uniform distribution, take from an exponential distribution. And so here's the question for this model. What's the probability that x majorizes y if the entries in x and y are chosen from an exponential distribution? And we can pretty easily actually figure out the answer to this. So we're going to let these c sub i's be the random stopping points during the race. So that means if we go back to that first picture where I showed x's positions and y's positions, and we just look at any time there's a stopping point for either of the racers, those are going to be the CIs. Now, since exponential distributions are memoryless, what does memoryless mean? It means that when you're picking something or when you're waiting for an exponential clock to go off, it doesn't care how long it's been since the last ring. So each of these CIs is equally likely to be a position of either contestant X or Y. So this is strange. So then we can take the up-down sequence H, defined to be U if CI belongs to Xavier, and D if CI belongs to Yushi. And we're back to up-down sequences. And because of this memoryless, this up-down sequence is uniformly random. Yeah.
Is an exponential distribution?
So it's, it's a probability distribution is just a function whose integral over the whole domain is 1.
Yeah.
And so if you use an exponential distribution to pick the coordinates, it's a little bit more technical than I have in the slide, but when you pick the coordinates from this exponential distribution, which will look exponential if you graph it, then it has this property that when you sort the elements chosen from the distribution, the distance between the elements is independent of where you are. That's it's like kind of how to say it, and that's this memorylessness. So when we're picking these stopping times, we can, instead of just, I guess, believe me that with exponential distributions, if you have picked the times for x and you also picked the times for y from the same distribution, and that distribution happens to be memoryless or exponential, then that's equivalent to just picking the stopping points in total, and then going through and picking, does this belong to x or does this belong to y? Does that make sense? No.
That's okay.
It's just a property of exponential distributions. Okay. So, well, do you at least get the statement, even if you don't understand why?
Yeah.
Okay. Does everyone understand the statement? So that means that Xavier leads all the way. So once we've defined this up-down sequence, Xavier leads all the way, so x majorizes y if h is type 2. So this sequence is ups and downs, up if it corresponds to this one, down if it corresponds to this one. And we want Xavier twin, so h has to be type 2. But from that earlier proposition, we know that exactly 2n choose n of the 4 to the n length 2 up-down sequences are type 2. So there are 4 to the n ways that I can pick an up-down sequence here. For each of the 2 to the n positions, there are 2 choices. And I know that there are only 2n choose n that are type 2. So my probability, again, is 2n choose n over 4 to the n, which is wild. It's independent. Well, it's the same as the uniform case. So then we started thinking, well, if the exponential model and the uniform product model have the same answer, then maybe it doesn't depend on the distribution at all. But that's wild, because the way that we prove these two things do depend on the distribution, right? I use this weird fact about exponential distributions to say that it's memoryless, and that we could do this thing. And the same thing with the products. I used that the lemma that said the ratio of uniforms is uniform if you condition on the ratio being less than 1. So there has to be something else going on under the ground, and there is. So here's the independence of distribution argument, and the answer, and the puzzle's answer. So regardless of mu, as long as it's a continuous probability distribution on R, if the n entries are chosen from mu, then the probability that x majorizes y is 2n choose n over 4 to the n. So it's the answer for the exponential case and for the partial products of uniforms, which, when you really think about it, is just partial sums for taking the log of the uniform. So if you take log of the uniforms, we turn those products into sums, and then it becomes this case again. So both of those have the same answer, and that's the puzzle's answer in general. Okay, so how do we prove this? We're going to simplify it a little bit by, instead of looking at x and y separately, we're just going to take the difference of x and y, and instead of looking at a random or an arbitrary probability distribution, we're going to look at a symmetric distribution, which is what you get anytime you look at the distribution given by the difference of two variables taken from some distribution, you get symmetric. And that comes from just like the convolution of two variable with its mirrored image. And so we got the ballot property. So a sequence Z is called ballot if if Z majorizes 0. So this is equivalent to saying that X majorizes Y if X minus Y is equal to Z. Just subtracting it to the other side. And here's the symmetric generalization. If the n entries in Z are chosen from sigma, the symmetric distribution, instead of the continuous one, it's continuous and symmetric, then the probability that Z is ballot is 2 entries n over 4 to the n. And in order to do this, we have to kind of stop talking about distributions because it doesn't matter, the distribution doesn't matter. So somewhere underlying is something that doesn't talk about distributions, and here's what it is. So we're going to say a set of real numbers is generic if its elements are algebraically independent over Q. So what this means is that if you have some linear combination of these elements and the coefficients are in Q and it's equal to 0, then all the coefficients have to be equal to 0. It's kind of like linearly independent over like a vector space, but it's not a vector space. And so here's the theorem that implies theorem 2, which it then implies theorem 1. Is that the number of ballot sign permutations of a generic set is independent of that set. So what is a signed permutation? It's a permutation of the set where we also put signs, and I'm going to write that out in a second, but I want you to see that this theorem implies 2 because the probability of this being ballot is just that you if you have a generic set and you look at all of the signed permutations and we count the number that are ballot and we divide by the number of signed permutations, then we get this probability. So as long as we prove that the number of ballot signed permutations is independent of the actual set we pick, then we know that the probability doesn't depend on the distribution, it doesn't depend on the numbers themselves. So this is the tricky thing. So here, this is the theorem again. And let me just define some things here. So a sequence S1 through Sn is a signed permutation of a set A if there's some permutation in the symmetric group Sn and a signed sequence of +1s and -1s, epsilon I, such that Si is equal to epsilon I times A sub pi of I. So we just permute these elements and we also stick negatives on some of them. And that's a signed permutation. And we're going to denote by B of A the number of ballot sign permutations of A. And the last thing we need to define is this A weight of I. So we're going to sum over this index set I all of the numbers that are indexed in I. So given a set A, we sum the elements in I, and that's the weight of the set. And we say that two disjoint sets, I and J, which are the index sets, form a collision if they have the same weight. So if you have a generic set, because it's independent over the rationals, it's not possible to have two, it's not possible to have a collision. It's not possible that any two index sets have the same weight. Because if they did, then there would be a non-trivial linear combination equal to 0. So just keep that in mind. And so here's the proof outline of 3. So I'm going to give you the outline, then we're going to look at some of the steps. So the first thing to note is that changing a single element of A does not change B of A. This is the first thing we're going to prove. So if you move one element, it doesn't change the number of ballot sign permutations. And we're going to do that by showing two things. The first thing is that changing one element will cause at most one unique and discrete collision. So if we change one element and we get a collision, that can only happen once, and it only happens in one place. That's the first thing. And the second thing is that we can biject the ballot sign permutations from before the collision to after the collision. So with these two facts, changing one element doesn't change B of A. Okay? And that's kind of the hard part. The second part's easy. So any generic set can be attained by individually changing the elements of another. So if I have one generic set, I can do this process however many times there's an element in the set until we change one to the other. And because we proved that, and that will prove that B of A is independent of A. And it just depends on A, the number of elements of A. We good with the statements? Okay. So let's do it. So here's, let's see, an argument for why changing one element will cause at most one unique discrete collision. So say our set capital A has A1 through AN, and we're going to change the first element, A1, by some small number delta. And now assume that we don't have a unique collision. So we have two pairs of index sets, ij and kl, for which the weight in the new updated set of these two pairs are the same. But then that means that I should be able to, up to ordering the I and j properly, that the difference of 2 and the difference of these two are both delta. Right? Okay. So if they are different, then there has to be some I in either I, j, k, l, or I intersect l, or j intersect k. And that just comes from contradiction. If there isn't anything in these, then it turns out that these two sets are the same. So the uniqueness, or the violating uniqueness is what gives us that there's some I in one of these sets. But then that means that A sub I, this I that we know exists here, has to have coefficient +1 or -1 or +2 or -2 in this equation, which contradicts that A is generic because we now have a non-trivial linear combination of these elements summing to 0. Okay, so that's the first part. Changing one element makes things change, will cause at most one unique and discrete collision. And the second part is we can biject ballot sign permutations before the collision to after the collision. So that means if I'm keeping an eye on a ballot sign permutation and I move one element, which messes it up, then that one ballot sign permutation, or that one sign permutation will stop being ballot, and another one will start being ballot. And so they just kind of, as soon as one flicks off, another one flicks on. So we need to figure out what it means, how do we take the one that stopped being ballot and change it to the one that now is ballot. So we're going to do this. So if a particular sign permutation remains ballot, well, leave it alone, we'll keep it the way it is. But if it is not anymore ballot, meaning that the partial sums are not all positive, then that means there's a unique value k and j less than k such that this turned negative. Okay. And somewhere in this sum is A1. Because we moved A1 somewhere in this sum. I mean, if A1 isn't in this sum, then this one couldn't have messed up. But because A1 was here somewhere and we've been lowering it, the sum can become negative. And it's just important to note that A1 does not have to be the kth element of this sum. It can be somewhere further back that, and it just kind of came down and just moving this by a little brought the whole thing negative. So, and then it's the really cool thing. So we can take this ballot sign permutation S that is no longer ballot and reverse the first k entries and make them all negative. And now this new sign permutation is ballot, and you can prove that it wasn't ballot before. And it's easy to actually show that, because if this thing was positive, now the first k, the sum of the first k is definitely negative when we move it back. So it wasn't ballot before, and you can show that all the partial sums of this thing are now positive with this updated value of a. Okay. So this completes the proof. So we translated things from distributions to generic sets, and then proved something cool about, well, at least what I think is cool about generic sets. And it leaves a couple of open questions. I have two here, and I have another one that I want to talk about. So one is that of higher dimensions. So there are lots of ways that you might want to expand this to several dimensions, but this is one that actually works. So if A is a random n by n matrix with entries from a symmetric distribution, sigma, what's the probability that the row sums and the column sums are both valid? And we can use the proof that I just showed, with a slight modification, to show that this question, although we don't know the answer, is still independent of the distribution. So just a small point back here. Theorem 3 doesn't necessarily imply theorem 2. We also needed one example. So theorem 3 shows independence, and theorem 2 includes independence and also the number. So we needed either the product of uniforms or more easily the exponential distribution case. Or you can actually just argue it combinatorially, which is my favorite, but it's kind of annoying to do. So for this higher dimension generalization, it can be modified to work, but we don't know this invariant probability. We do know asymptotically, so 1 over, so 2n choose n over 4abn. This is asymptotic to 1 over root pi n, and you get this from Stirling's formula. But because the row sums and column sums are positively correlated, this answer is not going to, this answer is going to change. Because right now, there's no correlation. Well, there is some in the sums, but now we're adding correlation. So owing to positive correlation, the answer has to be between this and 1 over root pi n squared. It can't be bigger than that. But we just don't know, or it can't be smaller than that, sorry. But we don't know where in between it is. So if you have any ideas, let me know. And the other open question is comparing partitions of n. And this is actually where everything started. So if you don't know, a partition of n is a sequence of decreasing, or no, not strictly decreasing, but weakly decreasing integers that sum to n. And they're written like this, lambda 1, lambda 2, partition n. So we want to know the probability that lambda 2 majorizes lambda 1. But in this case, it's not going to be possible to majorize. This triangle doesn't mean strict as it did before. It has to be majorizes or is equal to, because the sum of two partitions are the same, if they're the same, if they partition the same amount. And this answer, if so, actually, this got solved very recently. So I actually have the answer to this. When the partitions are ordered. So if you don't care that it goes 3 plus 1 plus 1, and you would count this as a different partition than 1 plus 3 plus 1. So normally this is what people mean by partitions, but if you talk about ordered partitions, or ordered number partitions is what people say, then we know the answer for this. And it somehow, miraculously, is the same answer, except there's a factor of 2. So it's 2 times 2 minus 2 n over 40. But we still don't know about the original question, so the one where you only considered the sorted versions. And it's incredibly frustrating because there is a sequence in OEIS that gives the numerator of this. So this probability is going to be some sequence of n divided by p of n squared, the number of partitions. And the numerator has a sequence on OEIS, you can go look it up. And it doesn't have a closed form, nor does it have a generating function, nor does it have any asymptotic approximations. So that is kind of what we're currently working on, is trying to use methods that were similar to how Ramanujan proved the asymptotic formula for partitions in order to get an asymptotic bound on this probability. So I think that is it. Thank you. Any questions?
Is this like, what field is this in?
So this is combinatorics and probability. Yeah, so it's, like I said, I don't know if you're here, but it's very different than the math that most people at Stony Brook do. Samira and I are the only ones who do it here. My favorite thing is to take a probability question and to turn it into a combinatorics question. And use enumeration principles to solve questions about probability. But there are lots of different branches of probability that you could possibly go into, and one of them is like more like calculus, and the other one is more like counting things. And I'm more counting things.
I don't really know much about like either, but combinatorics, is it more dealing with like discrete, whereas probability is more continuous?
Yeah. So I think one of the crazy things about this problem is that you take a continuous question and you translate it into something discrete. Because in a continuous probability distribution, the probability of anything happening, if any one thing happening, is 0. Right? I don't know how much measure theory, I don't know how much measure theory you all know, but the probability of one thing happening is 0. And so somehow, magically, discrete problems and continuous problems can have the same discrete answer. If you look at them the right way, which is the point that if you ask this question about this random race, you're not looking at it the right way. The right way is with these generic sets.
Also, like what we were saying before, where it's like you're looking at the different types of distributions, you're getting like different answers, but you realize that like there was this general pattern that it didn't really matter. Like, how do you like get to a point where like if you see it in different ways, you get different answers, and like isn't there like supposed to be like one right answer?
Go back here. So I'm not sure I fully understand your question, but let me say something that might answer it. If this is the question that you are given, like as a research question, to prove, or to even think about, like if this is a question, is this probability equal to that? Or what's the probability? The first thing that I would do is open my computer and program something that I can tell it the distribution, and it would tell me the answer, and see what the answer is, and that's what I did. And then if you get something nice and you change the distribution and you get the same thing, that's when you start thinking, there's something going on here. So not every question relies on the underlying distribution that you choose. And there are actually a lot of questions. Like that. Another famous one, well, not famous, but another one is if you have a bullseye, or if you're playing darts, and you throw a dart, and every time you throw a dart, the place it lands defines a circle, and you color that circle a particular color. So something like this. So you have a circle, hit a dart, and there's the center, and so it determines this, and you do it again. And when you do that bigger one, because you color the whole thing in, you don't see this circle anymore, because it covered up the previous one. But if you go inside again, then you get. And after n dart throws, the question is, what's the expected number of circles you see? And that is also independent. Several distributions give you the same answer. So not always, like, there is one answer if you ask the question properly, but it doesn't always depend on the distribution. Is that kind of? Any other questions?
Will these slides be available after?
I can make them available. Sure.
Yeah, if you send them to us, we'll figure something out. And you can also send an email to Matt as well.
No more questions?
No.
Okay, well, that's that. Thank you.